So this is a problem from chapter 7, and the question, this right here is enough to sort of know what to do. But my question to you is, do you have any idea how to start this problem, or what would be your first step to integrating this definite integral? It's okay if you're not sure.
Well, the first step would probably involve trying to find the actual integral.
Yes, but before that, there's a small rewrite step that might be useful here. So for example, this is really x to the -2 power. And you can always rewrite, and this helps when you're finding the antiderivative or the integral. Now, off to the right here, do you recall when you have x to the n dx, like let's say it's x squared, do you remember what this becomes when you find the antiderivative?
Yes, it's essentially the opposite of a derivative. It's x to the n plus 1.
Yes, with just a tiny bit more, you divide by the new
divided by
exponent. The new x. I call it the new exponent. It is n plus 1, but since we don't know what it is, I tend to do that. So that is applicable here. So this first one will become x squared over 2 plus, and then depending on your comfort level with just performing the arithmetic here, you might be able to immediately tell me it's this. You might be able to move the minus there where the plus sign is. But we'll consider this finished. How do you know what to do with the 1 and the 2, the bounds, the integral bounds here?
Yeah, you essentially just plug both of them in and subtract the answer for the 1.
Yeah, exactly. So it's top minus bottom. All right, so we would go 2 squared over 2, and I'm going to rewrite this as -1 over x because it just fits a little better. So -1 over 2 minus, now this is now the bottom part, and I put it in parentheses because we might actually need to add or subtract. We'll see. 1 squared over 2 and then distribute in the negative, -1 over 1. Okay, and then from here you just perform the arithmetic. You get the number essentially. So this is 4 over 2, that's 2, minus 1/2. This is 1/2, so when you distribute the negative in, it's also minus 1/2. This is -1, but that makes it +1. So you have -1/2, -1/2, +1. Those all go away. So the final answer is 2. So from here, the way this format works is, and it's totally up to you because you're the customer, you're the student here that's trying to learn. I can give you one like it, which I would recommend, and either have me work it out again, or you work it out, or if I work out another one, then I have you work out one. That is kind of the best way that this format goes. Or if you're like, hey, Matthew, you know what, I got it down, then we just move on to a new topic. So what would you like to do here? Give you one like this to try, or have me work out one, or move on to a new topic?
I think I have a pretty good understanding of how basic integral works.
Okay. So that is like the most basic question in this section, just to like throw that out there. Okay, so let's move on to a U-substitution problem. All right, so I am sorry, that is not a U-substitution. Okay, let's do this one right here. All right, so this is a U-substitution problem, potentially. All right, do you have any idea what the U-substitution would be in this problem?
It would most likely be the 3x plus 4, but it could also be the entire.
Yeah, this is actually the appropriate one here. It's, if you haven't seen a list, it's usually like exponents would be one of them, in parentheses, denominators, under roots. Really don't know. You basically have to take a step and try it. Your derivative on the left is du. Your derivative on the right is 3dx. You generally solve for dx. Again, if you've seen this all before, just let me know. But where I'm going to help here is remind you that the best way to do this, I'm going to put this as 1 over and imagine the dx is over here for the moment. Instead of writing the cube root of u, you would want to change that to u to the 1/3 power. You want to be really comfortable. You want to remember, oh yeah, that's to the 1. That's why it's 1/3 power. And then instead of dx, it's du over 3. And you rewrite the integral enough until you're like truly comfortable with like, hey, like you can integrate it. So keep simplifying it until you're really comfortable. Like you can put the 1/3 on the outside. This becomes u to the minus 1/3 du. Is that clear?
Yeah.
Okay, great. So if that's clear, then the power rule here says you add 1 to this. That's u to the 2/3 over your new exponent. Or I'm sorry, you write your new exponent on the bottom. Okay, and then there's always plus c.
Mm-hmm.
Okay, now you may feel like you're done here, but there's probably 2 things you should do. The first is you definitely have to back substitute your u in, so that original substitution you made for 3x plus 4. The other is that you need to simplify
the 1/3, 2/3.
Yes. Yeah, so that's where some students, if you're not solid with your previous courses, you can run into some issues here. Like this flips up here, it becomes 3/2 times 1/3. It's 1/2, and then u is 3x, what was it, plus 4 to the 2/3 power plus c. Anything about this you would like me to review again with you?
No, that one was pretty simple.
I think you got it.
I think
Okay.
it's the more complicated U-substitution ones.
Absolutely. Yeah, we're going to do one next. I just wanted to make sure that was somewhat clear before we go in there. So the truth is about U-substitutions is if you guess wrong, the problem gets worse, not better. And the other thing is that when you apply your U-substitution, the integral needs to be something you know how to do. You have to, you're trying to make the problem simpler, which is why you make the U-substitution here. A third part is that the derivative of the u should already be in the function. So there's a lot there, but if you do enough practice, you eventually see the pattern of like, oh, it's probably this, let me try it. And you don't waste that much time if you're wrong. So any guesses here as to what the u should be for this particular problem?
Maybe tangent 1 over u, but 1 over theta, but I'm not sure at all.
Right. So if you try that, okay, and that could work here, you would, when you take the derivative of tangent, what is the derivative of tangent?
That's secant squared.
Right. And it's kind of in there, but it's kind of not. Like it isn't perfectly in there. It generally needs to cancel out unless we're doing an unusual problem here. So sometimes, simple is better than not simple in this case. So this is really theta to the -1 power, but du here, take the derivative of this 1 over theta, or theta to the -1, it's power, right? It's minus theta to the -2 power d theta, but it's generally better to write it like this, especially since we're going to substitute it back in. And that's the speed with which you really need to be comfortable doing this to be able to execute on the AP. And you can get there if you're not there already. So you substitute in, try not, like my method is not to try to make cancellations. I leave what I don't know. I don't know that 1 over theta squared about anything about that. So I just leave it. But I know that 1 over theta is u, 1 over theta is u, and you always substitute in for d theta. So if you solve this for d theta is minus theta squared du. So this becomes minus theta squared du. And look at that, the theta
cancels out.
Yeah, and you need to get rid of the original variable completely. If you don't, you've made a mistake. Generally, that's 80% of the time, 90% of the time. Minus secant u tangent u du. This is a known integral. Do you have a table of integrals that you like, or table of derivatives?
I do not have that.
Okay. Now, it may seem like an odd question to ask, but I'm big on reference sheets. I'm going to send you one through the chat here that I really like. It's from a university in Texas, and they do a really good job with their calculus course. Let me throw it into the chat. And it's on page 2 are the integrals. So this is one of those that if I'm an instructor, I definitely expect you to know. But sometimes they just give this to you. So this becomes, and I'll snip it in here on page 2. So this becomes just secant. So this becomes minus secant u plus c, always plus c. And then again, you got to back substitute your u. Very often this gets forgotten, especially the first time through the course, because just you're doing so much here that just hard to do. So, and the other thing here is that the derivative of this function is your integral. Like if you were to take the derivative of this function, you should get what you started with.
Mhm.
You don't have time to do all that in the exam, but but that would be possible. Like it's a nice thing to do if you have infinite amount of time. All right, so let's try another one here and see if this one is any better or clearer.
Okay.
It is nice to know we're not preparing for a test. A lot of times that's the nature of the lesson, and it's hard to get clarity when you're trying to compress everything. So, but this is definitely a U-sub problem. Now, remember, I'm telling you that, and on the exam, you would just be given this integral and it'd just say, find the antiderivative or integrate. Like you
Yeah.
wouldn't know that that's a U-sub, but I'm telling you. So take a look, give me your best idea
E to
of what,
the x.
yeah, it's e to the x here. You know that du is e to the x dx. So this resolves to secant u du. Okay, now this one's kind of right on the edge of like, would you actually be expected to know how to do this one? Since you have a permanent substitute teacher, that's a tough question to answer, but this one's a little harder to remember. That's the antiderivative of that. So if you think you'd have to remember it, look at it, do whatever you do to remember it, but it's a little bit on the edge of case of being a worthwhile one. So, all right. Sometimes problems can appear to be U-substitutions, and they're actually not. So let me show you a problem like this. We get so wrapped up into actually like doing U-substitutions that we miss things that we should already know. So I call it a rewrite step, and rewrite generally means like you're applying algebra. And in this course, it's usually like exponent rules, factoring. And if you do one of these things, it helps to make the problem simpler. So like here, t, this right here is really, it's 1 over t times t to the 1/2. So it becomes the integral of 1 over t to the 3/2, which becomes the integral of t to the -3/2. And maybe that was obvious to you, but when you do the way we do things, and when you pattern things, like if you do more than 2 things in a row a certain way, you tend to think the third one is that way. And this one is not. It's just a straight power rule integral.
Yeah.
Okay, so would you like to spend any more time on U-substitutions?
I wouldn't mind trying to do one myself.
Okay. Would you like easy, medium, difficult?
Medium or more difficult, probably.
Okay. I think this is This one is maybe more difficult because of the evaluation of the endpoints, but let you take a look at that one. So I'm just going to mute myself for 60 seconds. Give it a try. I'll check in. I'll definitely help you work this out if you're not sure, but give it a look, please.
Okay.
Hey, Natasha, how are you doing on this one?
Not too bad. I would guess that the u is tan x because the derivative of tangent x is secant squared x.
That's a good choice. Works out great. Now, question for you here. Did you change the limits of integration when you made the substitution, or did you back substitute when you were done?
I have not gotten that far.
Okay, sorry. All right. It's one of the disadvantages of doing it this way is I sometimes don't know how quickly you're moving through it, but yeah, carry on, I guess, and I'll check back here in another 30 seconds or a minute.
Okay.
All right, I am back here. I'm going to continue working through this problem. Let me know when you're available.
Sure.
Okay, so hopefully you got to this antiderivative. If you back substitute the u, you get this up here, which is e to the tangent of pi over 4 minus e to the tangent of 0. Tangent of pi over 4 is 1, so this is e to the 1 minus tangent 0, 0, like this. Now, alternatively, and this is the direction you want to go as you move through this course, because you actually do change your bounds quite often when you're integrating, is you can actually evaluate the two endpoints, u of pi over 4 and u of 0. And there's certain problems where it just helps quite a bit. So for example, your tangent of pi over 4, and this is like knowing your unit circle, is 1. Tangent of 0 is 0.
Mm-hmm. So essentially just evaluate the endpoints beforehand.
That is one technique that, like, if it's like one of those things where if, like, if you could just buy into it, like, remember the first time you learned radians and you were used to using degrees and you're like, I don't want to use degrees, I don't want to use radians, I want to use degrees. And eventually you just got more comfortable doing it. Well, if you accept that it's better to change the bounds on this, the problems do ultimately become slightly easier, because now you're evaluating e from 0 to 1, and that's a little bit easier to do. Now you get the same answer, and that's the point I wanted to make here. You get absolutely the same thing. It's a choice. As you take more math, like as a high school student taking AP calculus, maybe you're going to take a lot more math, and these are just techniques that will help you further along.
That makes sense.
Okay. Would you like to do any more U-substitution problems?
I can move on.
Great. The next main topic in this chapter is integration by parts. There are three, I call them types of integration by parts problems. The first one is going to be an integral of some sort of polynomial of x times, and it's an option here. It's either an e to the x, a sine x, or a cosine x. And if you recognize this type, you always do the same thing when you're integrating them. So for example, if I asked you to integrate x squared e to the x dx, this is what I mean by a type 1. The polynomial function of x is x squared, and then you've got an e to the x as a choice, like you're choosing one of these three functions. Okay. Now, when you're given this type, u is always the p of x. So our u is going to be x squared. dv is always the other thing, e to the x, sine x, cosine x, and you carry that through for the entire problem. Like if you end up doing integration by parts again, which you actually do here twice, you would use the same types of substitutions. So your dv is e to the x dx, and you have to integrate that. So on the left here, du is 2x dx, and on the right, v is e to the x. A small point here. Sorry, I'm throwing so much at you. Sometimes, like I want to get it all out because there's so much like good stuff here to share with you. The you can take a derivative of everything. You know how to take a derivative of every single thing that ever exists, believe it or not. But there's only certain things that you know how to integrate. So when you're choosing these, let's just say you get to a test or some problem, you can't remember what I said. Maybe you'll remember that if you can't integrate it, that means that it was the wrong choice. And we'll see that in a different type of problem here. So just keep that in mind. So your formula for integration by parts is uv minus the integral v du. And you literally just combine the thing. So it's x squared e to the x minus the integral e to the x 2x dx. Just putting those in each position. I assume you've seen this before.
Yeah.
So now you get to this new integral, and it's not that it's always integration by parts again, but you look at it, I'm just rewriting it here. You look at it and you say, well, is it something I know how to do? Is it a U-substitution? Is it a table integral? And the answer is no, it's not. It's integration by parts again. So you set your u to be this polynomial function, include the constant if there is one, and dv is e to the x dx. So du is 2 dx. And you integrate both sides over here, v equals e to the x. You do your uv minus the integral v du. Now keep in mind, this is like in brackets. So when you're subtracting here, you have to account for that sign change. Minus 2x e to the x. And then this minus goes with this minus plus integral e to the x 2 dx. So this last one here is the 2, you can imagine the 2's out in front. It's just 2 e to the x plus c. Don't forget that. I've seen teachers just fail students for not putting that on their exam. Okay, let's do another one. We'll make it simpler though. Let's say you're doing the integral of 2x plus 1. And let's go sine x dx. So this is that type I was mentioning up above. It's some sort of polynomial, and then it's an e or a sine or a cosine. So your u is always the polynomial 2x plus 1. Your du is 2 dx. Your dv is sine x dx, integrate both sides. What is the antiderivative of sine, if you know?
Antiderivative of sine, I believe, is negative cosine.
Yes. Now, sometimes as an early calculus student, you might even write this pattern of like when you take derivatives. So sine leads to cosine, cosine leads to minus sine leads to minus cosine, and then you flip back. So you just like figure out where you are in that list. And like you said, you go to the other direction. This is minus cosine x. There's a lot of these things that happen in this course. So it's uv minus the integral v du. Got to know that. 2x plus 1 times negative cosine x. So I'm going to put that negative out in front, cosine x minus integral. So minus cosine x will make this positive, cosine x. Sorry about that. All right, so then that's dx. Okay. And notice here that this is not an integration by parts anymore.
Mhm.
It's just a straight, like, find the antiderivative of cosine. The antiderivative of cosine is
Sine.
sine plus c. And then as far as simplifying, really doesn't matter. Like at this point, like you're beyond that. I mean, maybe instructor will say, you know, I want you to simplify, but it's generally accepted. Like the calculus is what they want your attention to be on.
They don't care about as much about the algebra. They care more
No.
about the calculus.
That's right. That's right. And you saw it with derivatives, I'm sure. All right. So that's type 1. Type 2. And these are my types, by the way. You're not going to see these in books, but they almost all fall into this category. It's like type 1. It's an integral of a natural log of x. I'm sorry, it's a polynomial of x times a natural log of x. And in this type, your u is actually natural log of x. And the reason is because you know how to take a derivative of u, but you don't know how to take a derivative of I'm sorry, you don't know how to take an antiderivative of natural log of x. So dv of x is p of x dx this time. So if you ever get this type, you do this. So here's an example problem to think about, or we can work out together, is just a standard like x natural log of x dx.
Okay.
Okay, so here the u is natural log of x, and the du is 1 over x dx. And the dv is, as I mentioned, it's x dx. And it feels like we're going the wrong direction because when you integrate, you get a 1/2 x squared over here. And you're used to in the previous type, like you want the degree of the polynomial to go down, but here it went up. So it feels like it's wrong, but that's why I'm telling you, like when you get this type, do this, it works. So let's do our substitutions. uv minus the integral v du. Natural log of x times 1/2 x squared minus integral of v 1/2 x squared times 1 over x dx. Are you able to follow all the substitutions I'm making?
Yep.
Great. So this is 1/2 x squared natural log of x. Don't have to do that. I will rewrite the integral though, because the x's cancel. This is just a rewrite step. That x cancels that x. It's 1/2 x dx. So the antiderivative of that, that's power rule. So it's 1/2 x squared. Your new exponent is 2. You could just combine those also, but plus c. That's your final answer. So so this is your classic exam question that they give you in this class. And it is the type I just did, except your polynomial of x is just 1 dx in this problem. Like there's literally a 1 there. And students often say, like, well, how do I do this? Well, you can literally make your dv just dx. Like it could be that trivial if it's the case in this problem. Your u is still natural log of x. So you got 1 over u, I'm sorry, u prime du equals 1 over x dx, and then v equals x when you integrate both sides. Okay, so that's x natural log of x minus integral. And then you see here you get x times 1 over x dx. So some textbooks actually include this as part of their, like they tell you that the integral of natural log of x dx is this thing on the left here.
Mhm.
All right. We can move on to type 3, or you can do a one of the x dx's where it's not the trivial case where this is some sort of polynomial, like, I don't know, I'll make one up if you want, but would you like to try one, or would you like to move on to the last type of integration by parts?
I'd like to try one.
Okay, perfect. So let's go with the integral of x squared plus 1 times the natural log of x dx. So I'll give you a full minute here or more. I'll check back at about 5:40 if that's okay. I'm going to just start writing out some of the steps here, and just go ahead and keep working. I won't talk, but I want you to see the steps here if they're needed. Natasha, when you're ready, take a look at the last line here and let me know if yours is any different. Yours might have a negative distributed to both, but it should have somewhat similar form here. Hey, Natasha, if you're talking, you may be muted.
I wasn't 100% done yet. I pretty
Okay.
much have the same thing.
Awesome. If you can do a problem like this, you're definitely understand how to do this type of integration. So I would like to move on to type 3. If that's okay with you.
That's fine.
Awesome. So type 3 is the integral of e to the x sine x or integral e to the x cosine x. And there's a couple of variations on this, like where they actually put numbers in front of the x or numbers in front of this x. But these are integration by parts twice. And then you always move a term around. Does that sound at all familiar to something you saw in class?
I think I know what it is, but I don't necessarily have anything that I can.
Okay, so you pick, do you have a preference here whether we do the one on the left or the one on the right?
Not really.
Okay, so I'll just choose the one on the left. Your u can be either. I tend to make u the trig function because it's easier to take derivatives of trig functions. E is always itself when you find the antiderivatives. Antiderivatives are always a little harder than taking derivatives. And you repeat this throughout. So like, since I'm making u the trig function, when we do integration by parts again, you want to make u your trig function and your dv your e again. Okay, so we got uv minus integral v du. This becomes, and let's do, so this becomes e to the x sine x minus the integral of e to the x, and then du is this minus cosine x. I'll make that a plus cosine x dx. This is no better, so we have to do our integration by parts again. U is cosine x. Du is now, I'm sorry, I made a, this is horrible. Derivative of sine is cosine, and that changes this right here. That was bad. Okay, now we got it down. Derivative of cosine is minus sine x. dv is, again, e to the x dx. So your v is e to the x. Again, the uv minus integral v du is in brackets. So you're going to have to distribute your minus sign. So it's minus uv. So it's minus cosine x e to the x. I'll put the e to the x out front. This negative goes with the next negative. So it's plus integral v du, but there's a negative there. So it becomes minus right there. Okay. And then if you're not paying attention, you missed the important step here, which is that this right here on the right is exactly what you started with. So and I never really found this all that, like, I didn't really think this was very, it was so non-obvious the first time I saw it. I didn't think that this could be how it is, but you essentially add this integral to the other side, which is not correct, but it's what you're doing. And so now you have two of them on the left. You have two integrals on the left. That's why you put the two out in front. And your right-hand side is these other terms that I'm just bringing down. To get to the integral part, you divide both sides by 2. Okay, so your integral e to the x sine x dx is e to the x sine x minus e to the x cosine x over 2, but then you have to have that constant.
Okay.
Yeah. Now I don't like this, but this is the form of this integration by parts type 3, or this type where it's an e and a sine or a cosine. You always do it twice. Generally, but not always, this last, sorry, let me get it right. This last integral is negative, so you end up adding it to the other side. It could be that you subtract. You got to be really careful with your signs. As you saw, I messed up the original derivative pretty bad here at the top. And, I almost introduced the wrong negative. But you always bring this term back over and then you divide. And that's your final answer. The only time you'll do these are on an exam. They don't come up in other courses unless you get a really higher end electrical engineering classes. You might see it again. Okay, so in that spirit, let's just look at a few and so my lessons go 50 minutes. I want to just put a few problems up and ask you the type. Is it, and our options are, it's like it's known. 2 is a rule. I'm sorry, that's a known. Another type is a U-substitution, or it's integration by parts. When you look at this one, what do you say here?
That's integration by parts.
It is. Let's look at another one here. So is this known? Is it U-sub? Is it integration by parts? What do you think here? Or maybe it's something we haven't covered yet. So do you remember partial fractions?
No.
Okay. This is a partial fractions problem. I was trying to see if you're like, hey, we learned that already. This is another partial fractions problem. We should probably pick up here when we start back. Let me give you one more and see what you think for this. All right, so is this a rule / known? I keep saying that it's known. U-sub, integration by parts, or partial fractions?
I'm not sure.
Okay, it is a U-sub. So let me show you that real quick here. Du is 1 over y dy. Do you see how 1 over y is in there? So it becomes the integral. This is cutting through a lot of the steps here, tangent of u du. And I mean, that's not great, but it is kind of a known one. If you go back and look, I think maybe we had that. It's a natural log thing. So that's like, rather than doing a bunch of problems, this is the last thing I was saying, we'll take a short break, is like sometimes it's good to just see if you know which type they are, and that way you feel confident with actually performing the mechanics of it. All right, so that does take us to the end of our lesson here. Please use the other booking email for our lesson here in 10 minutes, and we can just pick back where we left off here, if that's okay with you.
Okay.
All right, I'll see you shortly. Bye.
Bye.